let's continue predicting the number of products in, and we're going to keep using chlorination because that's a reaction that gives us multiple products. So now I'm complicating the structure a little bit more. So let's get to this molecule, for example. Now, this molecule has 2 chiral centers. It is interesting. So now let's classify the type of positions here that we will have and predict how many products we have here. So now this is the history, so that's a primary position, that's also that. By the way, this is a meso compound. But what matters here for the number of products, this position is primary, that position is primary. You will have one type of product, so B and C, B, but you have tertiary positions, so we're going to have D and D. So initially, let's draw the products that result from that. So replacing one of the hydrogens here will lead to the following. If I do replacing one of the A hydrogens, if I do that here, it will be the same. So now that's one product. Let's replace now one hydrogen type B. And if I do that, I will have the following. Well, here, this is interesting in the sense that when you form this radical, the radical is secondary, but once you do the replacement, you will have, remember that here you have 2 hydrogens. When you do the hydrogen abstraction, you are going to form this radical. That's secondary. But when you do the attack, you are going to have a product that actually has a new chiral center. So because you will have this constituent different to that and different to hydrogen. So these will lead to, this radical will lead to 2 products. And we are going to draw it. So these 2 centers you haven't touched. And here you will have replacing one of the hydrogens. We can go the attack from either side of the plane. So you can have chlorine and you can have one more here. So here, why? Because you're creating a new chiral center. Notice that here again, there is 3 substituents that are different, but you still have a hydrogen, which I pictured there. So this is attacking on the position C. So that was A, that was B, but B, you have 2. Let's do C. And I'm not touching this 2, so they will stay the same. At C, you have 2 hydrogens. Let's draw it like that at first. When you remove that one, you're going to make a radical. Let's do it. This radical, which is also secondary. And now, are we creating a chiral center or not? So we need to analyze that. So if you go this side and that side, they look the same. So you're not creating a chiral center there. And so you will do one substitution here. So the 2, say, substituents on this side and on that side, they look the same. So you're going to be looking at that product. So here I have this mix. Here I have 1 product, 2 products, another product. So this is replacing C. And remember that all of that, I said it was a monochlorination reaction. Lastly, we have the position D. Position D is tertiary. So in here, I want to draw the radicals. Say that I remove that hydrogen. This is the hydrogen abstraction step. Right, so when I do that, and I'm going to keep that the same way, but this one, after you remove the hydrogen, it is trigonal planar. What that means is that now you can have the attack of the chlorine radical from either side of the plane. That would lead to 2 different products. So in this case, this carbon will stay the same. But here you will have, for example, that and the enantiomer of that. And I'm gonna have to draw it small. So chlorine on lash, metal on dash, and this is still the same. So that center will have the, well, actually they're not enantiomers, I'll show you why. This the opposite absolute configuration, but here the center, which is also chiral, has not changed the configuration. So this two are related as diastereomers. Stereochemistry. Okay, this two. Because we had created this chiral center, had now racemized, it had a specific configuration, it lost it and gave two centers that are inverted, but still you're keeping the configuration of the other centers. So overall, notice how many possible products we were able to form. At the primary position A, you have that. When you extract hydrogen B, this one, now you're forming this trigonoplanar radical, and you can have the attack from either side of the plane. Just we need to remember if we are creating a chiral center or not. Here you know that you are, because when you look at these constituents, you see that you're generating something with 4 different constituents. So that center is, the two opposite configuration, but these two molecules are also not enantiomers because the other centers are keeping the same configuration. So even though this, you're creating a new chiral center, yes, but you had 3 chiral centers in this molecule. Now, when you extract hydrogen C, you're creating this product. Again, this is trigonoplanar, but now this, you're not creating a chiral center. So you have one product. And finally, when we did the substitution, hydrogen extraction at D, you're creating this radical. This, again, remember that we don't draw wedges or dashes anymore here because this is trigonoplanar. And you can have the attack from either side of the plane, so you're forming here this center with 2 opposite configuration. However, they are not enantiomers because you had another chiral center that has not changed the configuration. So these two are diastereomers.